So this is Unit 3, Lesson 11. And today's topic is if I have a magnetic field and if I have a charged particles, what is going to happen if it's moving that way? Okay. And just recall when it's a charged particles can be a plus or minus. And then I think we talked about what rules to use. If I have something that's positive, I would use my right hand rule to decide the directions. If I have something that's negative, I would use the left hand rule. And we are going to review that. And then it's moving through a magnetic field. So an example for that is if I don't know if you remember these dots and circles anymore. For examples, if I tell you this is your magnetic field, okay? So I'm telling you that the magnetic field, if your paper is on your table at this point, okay? And so I'm going to say this again. If your paper is on the table, and I show you that these blacks are the magnetic field, hopefully you remember that a circle with the dots means that the magnetic field is coming out of the page. What that means is it's going, like if you're in your room, if this paper is on the table, flat on the table, your magnetic field is going to be from the floor pointing upwards towards the ceiling. Okay? And hopefully you remember that this will be your fingers, right? So meaning if you have your palm open up straight, not curled up, open up straight, you should have your tip of your fingers pointing towards the ceiling. So that's the first step. Okay. The next one is that if I have a point charge, I'm going to assume that this point charge is a positive point charge and is moving to the right. Okay, and the rule is if I'm using a positive, I'm using my right hand. So the pen, if you're a right-hander, this is what you're holding your pen in. Okay, so that means, hopefully you remember, this is your thumb. Okay, your thumb is pointing towards your wall to the right-hand side. All right, let's see if you can figure this out. Okay, so open up your hand. Right now, your fingers should be pointing up towards the ceiling. So everybody, put down your pen, have your hand open up and pointing towards the ceiling. But at the same time, you have to twist your hand so that your thumb is pointing to the right, lining up with the red arrow. Okay, if that's the case, do you see your palm is facing towards yourself? It's going to the bottom of your piece of paper. So that means the experience of the FM, because your palm is the direction of the FM, the force, okay, wherever your palm is facing. So I found that the palm is facing downwards in this particular question, meaning as this proton is moving, it's actually experiencing a force that is going towards downwards, okay? And the new thing that you're learning, I actually think I did talk about this, but let's just recap, okay? The force will actually move the particles in a circular motion. So we're actually tying a lot of things together, okay? The magnetic force is actually causing a circular force. Oh, it's all joining together. Meaning this red path, instead of going straight, is going to be experiencing, because of the constant force that is acting on it, it keeps making it twisting, causing it to go in circle. Whoa, okay, all these things together. Okay, so let's recall. Okay, this is a point charge. The magnetic force of the point charge, I'm going to write it at the side. The magnetic force of the point charge is QVB. I'm actually going to drop the sine theta because this is all saying that the particles are perpendicular. So sine of 90 is 1. So I'm just going to drop that. Centripetal force, we've learned that is mv squared over r. Do you remember that? All right, so we're actually going to group them all together and figure out this new equation. All right. So let's go to the next page now. Okay, so the big thing is Fm is going to give you, it's going to cause the centripetal motion. And just now we already said, I recall, so if you want to write it out again or you already had it written out, I know that for a charged particle. Point charge is QVB, not ILB, not the one with the wire. Okay, and I know that centripetal acceleration is v squared over r, so this is mv squared over r, so they just plugged it into there. So you can rearrange the equation for r. It's telling you how big the radius would be if I have this moving charge at this speed. If this is the strength of the charge and if that's the magnetic field, that's how long it would work. All right, complicated pictures is this. Okay, so it's going to be causing. So the key thing I need you to get from this is your magnetic force is equals to your sort of circular force. Okay, super big question. Okay, all right. So let's read the question. If you need to pause the video, right? But okay, we're gonna talking about an electron. It's accelerated from rest in a horizontally directed electric field. Oh, we're tying electric field of all of these together. A potential difference of 46 volts. The electron then leave the electric field, enter a magnetic field. This is actually the second part of the question. The magnetic field of 0.7 T directed into the page. Okay, so two-part question. Okay, so I need you to add that basically in this right here, there's actually a parallel plate. Okay, and they tell you that you have this parallel plate that is going to take your electrons and it's going to accelerate it through the electric field. So this particular electric field is going to speed it up until it gets to the end of the electric field to acquire a certain speed. That's where this speed came from. Okay, we actually need to find what is V2. At the end here, what is the final speed? So V1 was 0. It got accelerated through the electric field, getting it stronger and stronger until the speed is whatever this V2 is. That becomes the speed that is entering the magnetic field. So it's two parts. Okay, so it's like kind of tying lesson 5 together with like lesson 10. Okay, so let's do the first one together. Okay, the first one I'm focusing on the yellow highlighting. I have an electron. Electron has a charge of negative 1.6 times 10 to the negative 19 coulombs. And I know that it started from rest. And I need to find out what is the speed when it comes out when the potential difference, this is the part you guys don't like, potential difference is delta V, okay, of 46 volts. Okay, so I don't know if you recognize that the question didn't say it out loud. This really is a conservation of energy question. Okay, so we have to go back to your equation sheet. I know that E plus delta EK is equal to 0. And negative Q delta V is equals to, okay, I shouldn't do this. Is equals to, I'm going to say add 1/2 mv2 square minus 1/2 mv1 square. That is the change in kinetic energy. All right, so I have my 1.6. I'm going to plug everything in. So this is 0. V1 is 0. So that's gone. So mass of the electrons, I didn't write it down, is 9.11 times 10 to the negative 31. Solve for V. Okay, 4.0 times 10 to the 6. Okay, second part, let's see what they're asking for. Part 2. is asking for what is the magnitude and the direction of the magnetic force. So they want you to calculate Fm. So Fm is QVB. You can put sine theta if you want. I'm just going to drop it. The charge is 1.6. The speed when it enters the field is, the magnetic field is 4.0. The magnetic field is 0.2. So I got 1.3 times 10 to the negative 13 newtons. Now the directions. Okay, if you need to pause the video, you could. I need you to figure this out. Okay, try to do it on your own before you check the answers. I'm going to explain. You can pause the video if you need. Okay, so couple of pointers. This is an electron. When it's in electrons, I use my left hand rule. So use your left hand. Okay, my thumb is pointing to the right hand side of the wall. So I'm going to have an assumption that your piece of paper is flat on the table. Okay, your thumb is where the electron is going, which is towards the right. Okay, your fingers, your open up palm fingers, the X represent that I'm actually pointing towards. So this is the magnetic field, which is my fingers, and it is going into the page. And if your paper is flat on the table, you should be pointing towards the floor. Okay, the ground of your house. Okay, so point your fingers downwards towards your feet, on towards the ground with your thumb. Oh, which hand? Are you using your left hand or right hand right now? Make sure you are using your left hand because we're doing any electrons. Okay, I'm going to repeat this again. Pointing your fingers from ceiling towards the ground. So my fingers are pointing downwards. My thumb is going towards the right hand side of the paper. My palm is actually facing to the bottom of the picture. So my palm is going down. Okay, this is where Fm is. So the direction is downwards towards the bottom of the paper. Okay. So finally, they want you to calculate the radius. So now that ties your Fm into your Fc. We found Fm to be 1.3. And as always, it's always a good idea to use the number that is left in your calculator. Okay, centripetal motion, mv squared over r. So finishing this off, m is in electrons. V squared is 4 times 10 to the 6. Sorry. All divided by r, which is what you're solving for. So I got r is equals to 1.1 times 10 to the negative 4 meters. Okay, so another typical type of question, right? All right, last one is concept. We already sort of talked about it when we were explaining the aurora borealis. Basically, you know that our Earth has a magnetic field, and we already talked about that our Earth magnetic field is going to be the strongest at the pole, right? So Fm is the magnetic field, right? Okay, it's going to be the strongest at the poles. Okay, so basically any charged particle that has a velocity that are parallel and perpendicular to the magnetic field in this spiral path. So they're talking about, this is the electromagnetic spectrum that we're talking about. Okay, because charged particle is basically electricity. Magnetism is the magnetic field. And in general, they move in spiral along the magnetic field line. and they usually spiral along field line that has the most concentrated particle at the north and the south magnetic fold. Okay, and then that's why you would have more chances of seeing an aurora borealis, because these charged particles from the sun will enter where the strongest magnetic field is, which is the north and south pole. And then we talked about that because the ion will energize the atmospheric particles, causing it to go up to a higher energy level, and then when it drops down, it releases light, which is photon energy, and that's a glow. Okay, so, and then we have this thing called the Van Allen belt. So it's just where it is. Okay, so basically at a very high altitude, our Earth actually have a magnetic field called Van Allen belt, because that's where the most intense over the equator, and it actually doesn't have it along, it doesn't have it along the poles. And what happened is these are the outer belt that actually have the particles from the atmosphere of the sun, and they spiral through the magnetic field, and it just happens to have two distinct regions that they just stay there. And because it has so much charged particles close to the Van Allen belt, satellites and spacecraft would tend to want to avoid these areas, because these charged particles can potentially damage any electrical equipment. Kind of like when we talked about the solar storm, same thing, right? When you have a surplus of a lot of charges particle, it can destroy delicate electronics equipment. Last one is this thing called the field theory. So it's a scientific model that describes forces in terms of field. Okay, this unit is talking about field. Field are not anything we can see. Field are not anything that we can really measure directly. It's always due to kind of the behavior of things when it experiences the field. Okay, so when objects, they don't actually touch. So atoms don't actually touch. Oop. Okay, these are the gap between the atoms and the electromagnetic forces that are causing the interactions of the atom in each of the object. If an object experiences a specific type of force, there is a field exists. It's like, I think in simple term, I think we get the gravity the most when we've been using this. If this is Earth, we have the gravitational field, but it's only if I have an object, if it's experienced the field, that it is going to move along with the field. That's how we can tell. But a field is like it's like an abstract substance. Okay, so then that's why they call it the field theory. Okay, and the field theory says electric and magnetic forces are more closely related to one another than the gravitational field. Okay, we've studied gravitational field. We've studied the electric. Okay, I shouldn't write that as a field. We have studied gravitational field. We have studied electric field and also magnetic field. The field theory is saying that the later two are more closely related to each other, mostly because of this thing called the electromagnetic radiation. And that's why they're kind of always grouped together, just because they're so closely. It's like basically if you have one, you always have the other. Because I don't know if you remember, right? The both theory of electromagnetism versus electromagnetic induction. If I have a moving electricity, I have magnetic field, or vice versa. If I have a changed magnetic field, I actually can induce current. That's how your generator work. They're just very closely related to each other. And the name of this theory is called field theory. All right, so we are done this unit studying the fields, and I hope you enjoy.